Hello everyone. In the last video we saw the inferences out of this particular curve. Let's try to do a meaningful inference again. So we said that any voltage which lies between 0 and VIL could be some 1/4 of VDD or something. Let's say VDD was 1 volt, so VIL will be 250 millivolts. So any voltage at the input of this particular inverter which lies between 0 and 250 millivolts will be recognized as logic 0. Okay, any voltage that is above VIH. So VIH, let's consider again 3/4 of VDD, which may be around 750 millivolts. So any voltage at the input side of the inverter which lies between 750 millivolts and 1 volt, that would be recognized as logic 1 at the input side. And similarly on the output side, we mentioned that if you see any voltage which lies between 0 to VIL, you expect the output to be high. Okay, any voltage at the input of the inverter which lies between VIH and VDD, the output is expected to be low or as close to 0. It is some finite value which is VOL. It could be VOL or it could be exactly 0, but somewhere which will be recognized as 0. So again, VOL which is present at the output, that should lie in the range of 0 to VIL. Okay, the VOL should be within range to 0 to VIL to be recognized as logic 0 at the next stage. Okay, it's as simple as that, because this is at first stage we are looking into 0 to VIL at the input. So the output of this will be again the input of some other stages. So the input of that particular stage should have a logic level which is 0 to VIL to be detected as logic 0. So hence VOL will be lying somewhere between 0 to VIL, just to be detected as logic 0 at the next stage. Okay, so let's move on. Let's look into a more practical curve. So for example, we have the VOH also. So right now let's consider the output high voltage, or the maximum voltage that is attained at the output of this particular inverter is VDD. Let's try to assume that now. We'll look into more practical curve which looks something like this. So this is again a curve which has been derived out of the inverter. Basically we take the probes and put it over here, and then plot this particular graph. Okay, and this is a more practical curve that you will be seeing at the output of this particular inverter. This was more close to an ideal one. It still had a finite slope because the most ideal one had an infinite slope. This is again close to the ideal one, which has got a finite slope. Okay, in this case we have a slope, but the curve is not as straight as this one. It has got these curves, and these are because of the non-idealities of the inverter itself. Okay, so again, if you see the slope which is present in the mid-range, this is still as negative value. The slope that you still see in the mid-range, it's still a negative value. Okay, now let us try to first draw the VIL and VIH, and plot the VIL, VIH, VOL and VOH on this particular curve. Okay, so for example, let's say this is the point, this is the minimum point that we see over here, that will be, or this is the input voltage level should be at least at this particular point VIL. The input voltage should be in this range to be detected as logic 0 at the input of this particular inverter. Okay, that is the first thing. The VIL which was present over here, it's present now over here. And if your input voltage lies in the range of 0 to VIL, your output is expected to be high. So this is not exactly logic 1, but somewhere around a margin which will be detected as logic 1. Okay, that is first thing. Second, any input voltage which crosses VIH and which is below VDD will be detected as logic 1 at the input of this particular inverter. And if you provide a voltage level in this range to the input of this particular inverter, the output will be detected as logic 1, as logic 0. It is not exactly logic 0, but it will be a voltage which lies in the range of logic 0, which will be detected as logic 0 in the next stage of the inverter. Okay, next is output low voltage. So what it says is, when your input voltage lies between somewhere VIH and above, you will expect an output which is close to VOL, and this VOL will be in the range of, it will be in this particular range. It will be basically below VIL. So why it makes sense to have VOL below VIL? Because this will be connected to another inverter or some other logic, and the input of that particular logic is the output of this particular inverter, and the input to be detected as logic 0, it has to lie in the range less than VIL. It should be within 0 to VIL. So VOL is a value which is less than VIL. Okay, makes sense. Next, you have the VOH. So in the case where VOH was exactly equal to VDD, in this case the VOH is not exactly equal to VDD, but it's a range. It's the highest value that is attained at the output of this particular inverter, that will be detected as logic 1. So where your input lies in this range 0 to VIL, your output is expected to be VOH and above. So anything which is above VOH, till VOH and above, it will be detected as logic 1 at the output of this particular inverter. And now VOH should be lying somewhere at the should be at a point which is greater than VIH, because the same reason, because this particular output of the inverter will be connected to another logic, another inverter, or any CMOS logic, and it has to provide a logic level at this particular input of the logic. It has to provide a logic level to the input of this particular logic such that it would be recognized as logic 1. So VOH should lie somewhere more than VIH. So keeping this particular inferences in mind, and also the slope that you see over here, it's close to -1. We expect the slope to be -1. And why -1? Slope is again the change in the output voltage divided by the change in the input voltage. So if you see, for this particular curve, the change in the output voltage, let's say it's falling from some, let's say some 900 millivolts to 800 millivolts, whereas the change in the input is from 100 millivolts to 200 millivolts. Okay, so change in the input voltage is positive. 200 minus 100, it's 100. Change in the output voltage is negative, and as a result of that you see a negative slope over here. Okay, it's dV out by dV in, and in the same direction. So if you go in this direction, dV output changes from 900 to 800. So change in the output is negative 100. 800 minus 900, and the change in the input voltage is positive 100, from 100 to 200 millivolts, and as a result of that you see a slope of -1. Okay, now with all these things in mind, we have inferred few things from this curve itself. The first thing is your VOL should be less than VIL, so as the next stage of the inverter should be able to recognize logic 0 at its input. And to recognize logic 0 at its input, we have made an inference over here which says that your input voltage should lie somewhere less than VIL. So hence VOL should be lying somewhere between 0 to VIL. Okay, next your VOH should be somewhere more than VIH. And the reason is again the same, because the next stage of the inverter should detect a logic 1 at the input of this particular logic. If there is a logic which is connected over here, it should detect a voltage level which is logic 1. So as a result of that, VOH should always be greater than VIH. Okay, with all these things in mind, what we'll do is we'll now plot all the voltage levels on a single line For example, there is a line which is just an axis. It starts from 0 volts, it ends at VDD volts. Let's plot it over here. So it starts at 0 volts and it ends at VDD volts. And now what we'll do is we'll take all this VIH, VIL, VOH and VOL and plot it over here and try to derive the noise margin equations from this particular curve. Okay, so what I'll do is, since we are already running out of time, let's try to plot this curve in the next video. Thank you.